Okay, welcome everybody. How's it going? Okay. We're in our final week. So we've got a few more things to cover today, tomorrow, and Wednesday. And then we'll have an exam on Thursday. Just as kind of method to provide extra feedback and whatnot, I'm going to plan to stay after today, on Tuesday, and on Wednesday. I understand people may not be planning for today, but if you want to ask extra questions or stuff, I'll stay extra, and we can do that. All right. If you have questions about the prior exams, if you have questions about your exams, if you have questions about the homework or things of that nature. Okay. But let's go ahead and get started. And I anticipate that we will probably have a little bit of extra time, or even we'll get through this material probably well within the 2 hours that we have allotted. Okay. What we're going to do though is continue our discussion on failure criteria. So last time we met, anyone recall the 2 failure criteria that we covered? Yes.
The Moore's and then the max shear stress one?
Okay, so we'll cover more today, but but it's related to the maximum normal stress theory. Okay, so we discussed how we can look at what's happening on a Moore's circle, and then transplant that over to a sigma 1, sigma 2 plot, or sigma 2, sigma 1 plot, however you want to call it, and kind of figure out if we're in the box or within the diamond. Okay, so in the box for the maximum normal stress theory, and within the diamond for the maximum shear stress theory, then we're good. The other way to think about it though is quite simply looking at a Moore circle and saying, okay, if my maximum normal stress is less than whatever the prescribed normal stress might be for maximum normal stress theory, then I'll be okay. And the same thing with maximum shear stress from a Moore circle, making sure it's less than a threshold. Now, one thing that maybe I went through pretty quickly because we were running out of time when we last met is what happens with uniaxial stress. And this might not be such a big surprise. I think we've covered it before a few times. But if I have a force pulling a specimen apart, as we have with our tensile testing, then we can figure out what the stress strain curve looks like, right? And often we approximate it as something like this, where this is stress and this is strain. Okay? And of key relevance, when we think about failure nowadays, we're interested in knowing when it is that we would cross the yield strength of the material. Okay? Now, in the lab, we were looking at ultimate tensile strength, okay? Because, well, the paper, the way it broke, and our sensitivity of our measurements, it didn't seem like we could really pinpoint easily a yield strength. Okay? So we just said, okay, we're going to go to the rate, the maximum stress that we get. We'll call that the ultimate tensile strength. But typically, when we're looking at systems with our metals or our ceramics, we're interested in thinking about what the yield strength is. Now, in the brittle materials, the ceramics, that yield strength is often really just the ultimate tensile strength because they fail catastrophically, right? And so there's not really this nice transition into plasticity. It's just bang. Okay. So if I have this uniaxial loading and I figure out what my yield strength is, if I'm using maximum normal stress theory, what do I compare to for maximum normal? So let's just say maximum normal stress theory, Okay, and I know that my material has SY, which is equal to, I could even say, the sigma ultimate under tension and the tension, or even the minus of the sigma ultimate under compression. Okay, what am I looking for here in my system? In order for, you know, for me not to fail, what is necessary? Right? Someone hands you a material spec sheet. Then they hand you the material too, but they hand you the spec sheet, and it has this, and it's a brittle material, so you think maximum normal stress theory. And they say, here's the ultimate tensile strength, which we'll say is a yield strength, or, you know, and we're assuming that the ultimate compressive strength and the ultimate tensile strength are the same, but of opposite sign. So how do we, you know, how do you compare? What are you going to think about when you have your structure and you're using your X-ray vision in that structure? What are you going to be thinking about in terms of, will this fail or not? Yes, Andrew.
The principal stresses,
Yes. Yeah, so the principal stresses and?
just comparing it to the ultimate tensile strength.
Right, you're going to be essentially saying, you know, is sigma 1 less than or equal to SY? Okay, that's pretty much it. Now you could even have sigma 1, sigma 2, sigma 3 all equal to each other, right? But as long as they're less than that ultimate tensile strength, you should be fine, right? And so, you know, on Moore's circle, whatever, you know, and this would just be for 2D, but let's just say that you had, you know, a 1, or this is a sigma 3, a sigma 2, a sigma 1, right? Something of that nature. We just want to make sure that this sigma 1, right, would be less than, right, that needs to be less than the yield strength of the material, right? And on a sigma 1, sigma 2 plot, I've got a box, right? And essentially this is going to be SY, this is going to be minus SY, SY, and you can say minus SY, right? For this, I mean, maybe it's better to do it like this: SY comma minus SY, SY comma SY, minus SY, comma SY, okay, like that, right? And so you just got to make sure you're in the box. Now, if it's a maximum shear stress theory, and we call this Tresca after the engineer. And I did my tensile test. What am I looking at here? What is of primary concern? What do you think, Josh?
The shear stresses.
Okay, so we're concerned about shear stresses. So I got to compare a shear stress to a shear stress, correct?
Yes.
Okay, so what is the threshold for shear stress? Meaning, like, what do I need to be? What shear stress do I need to be less than?
I forgot the name of the ultimate for the material.
Yeah, so it's a shear strength, right? Sometimes we call it SSY. Okay, that would be like the shear strength. And what is that equal to? So this is the threshold that we're comparing to. Look, Javier. What is the threshold? Yes.
The maximum shear stress.
Okay, it's a maximum shear stress, but how do I calculate it? Yes, Andrew.
It's the yield strength divided by 2.
Yes, so it's 1/2 the yield strength. Now, how did you calculate that out? How did you know that, Andrew?
I just remember it from watching the video, but I
Okay.
guess the more circle.
Yeah, right. So you remember it from a video, right? Or whatever, or your head, right? It's from Moore's circle. Why? Because what happened in Moore's circle? And this is the threshold that we get from which test? From the tensile test, right? The uniaxial loading. This is not like when you've designed your structure, you don't necessarily think that your structure is going to have uniaxial loading, right? But this is a threshold that we get to from the tensile test that we did over here. Okay? So this tensile test, that loading is going to have, right, a Moore circle that looks like this, where, this would be like sigma 2, sigma 3 essentially, and this would be sigma 1, and we now know about absolute maximum, right? Oh, that's a horrible circle. It's not that bad, man. Probably better than the one I'm about to do. Okay, that's not bad. Okay, so the SSY is there. This is just relating back to this loading situation. Are there questions on that? This stress right here, right? The stress that I have at break is because of force divided by area, right? And I know that I have a sigma 1 equal to force divided by area, and then sigma 2 and sigma 3 are equal to 0. Questions on this? Thoughts? What do you think? I've seen faces. Is it simple? That simple that it's like we're doing it? Okay. So it's because we're like, okay, I got it, right? So that's the uniaxial loading situation. That's how we figure out what SSY is. Okay? Because the radius of the Moore circle is just half of the SY. Okay? So when we compare now to, if we want to figure out if we have failure from the maximum shear stress theory, right? What we have to do is we have to calculate the shear stress in our system, right? So we know, and so probably the easiest way is to do another Moore circle, right? And whatever the loading is, maybe it's something like you're here, right? This is like a sigma x tau xy. And this is sigma, and this is tau. And this goes like this, and we have a nice little Moore circle, right? We've got to figure out what the radius of that is, correct? And going even further, if this, if there's a sigma 3 that's down here, for example, or somewhere else, okay, or maybe the sigma 3 is over here, right? We've got to figure out what the absolute maximum shear stress is, which is going to be corresponding to this down here. That's the tau max, absolute max, better said. Right? And this is what's this has to be less than the shear strength. Okay, any questions on this? And this, so if we look at it on a sigma 1, sigma 2 plot, okay, then what you have is something that looks, and it's not as symmetric as it needs to be, but oops, and it's not actually correct. Okay, but this would be SY, Y. This would be minus SY down there at this point. Okay, and then we have this line which represents pure shear, and it intersects here at this point at minus SY over 2, comma SY over 2. And over here, it intersects at SY over 2, comma minus SY over 2. Okay. So if you have pure shear, you're going to be on this line that has slope of minus 1. And if you look at your sigma 1 and your sigma 2, okay, it's going to be corresponding to this. So pure shear is an interesting situation. Let's just talk about that for a second. Okay, pure shear would be that you have your element, if we say this is X, this is Y, okay, you're going to have an element that looks something like this. And this is your tau XY. So pure shear, what does the Mohr circle look like for pure shear? What's that? What's that? So okay, so let's, here's your sigma, here's your tau. What does pure shear look like on this? Yes?
It's a circle right in the middle, right?
Yeah, it has its origin, or center at its origin, at the origin of the axes, right? And then tell me what to draw.
The minimum and maximum of the circle are at the number that is the shear stress that you have.
Right, so in this case, right, this would be a circle that looks like this, and this is tau xy. Okay, that's for the given load, right? This is, and we're going to talk about this a little bit, but you know, sometimes you're drawing more circles to describe the load, and sometimes you're drawing more circles to describe the testing that was done on the material. But if it's a testing, it's really usually only uniaxial loading, because that's pretty much all we know how to do in this class, okay? Which is fine. This is a great test. Okay, so that's the operating load. Okay, this is the operating stress. So then, in this case, let's say that we're trying to use our maximum shear stress theory. Okay. Tau xy has to be less than what? Well, what do we say here? It needs to be less than whatever our shear strength is. You see that? And we got our shear strength as being 1/2 SY. Okay, so the shear stress has to be less than SSY, and that has to be, and SSY is equal to 1/2 SY. Okay? Because that's what we derived from the Mohr circle for the uniaxial test, right? So that means, okay, that if I've got pure shear, then it's a done deal. I just say, okay, tau xy is less than that. But let's say that I'm drawing a sigma 1, sigma 2 plot. Right? Sigma 1, sigma 2 plot. This thing. Okay? So sigma 1, oh, did I draw? Okay, usually you don't draw sigma 2 going downward. That's because I was doing more circle. Okay, there's sigma 2 going upward. Okay. So on a sigma 2, or sigma 1, sigma 2 plot, let's do sigma 1, let's do sigma 2 like this. What does this mean? Well, first off, where are sigma 1 and sigma 2 for pure shear? On this, the Moore circle. Where are sigma 1 and sigma 2 on this plot? Yes.
You can find sigma 1 with 0, 0 plus the radius. It's whatever the
Yeah, so this is going to be the sigma 1, right? And then Kavya?
Sigma 2b at the origin.
So typically, typically we'll say sigma 3 is at the origin. Okay, I understand because that's a less one. But also another thing to keep in mind here is that the origin is not, in this, at least for this planar stress layout, it's actually, there's no stress there right now. Because and I could say, okay, there's 3D, right? But if I'm just looking at in plane, I've got only essentially two options. You know, I've got a pair, and they are all on the circle, right? All the pairs that function, whether they're tau xy and a sigma, or my sigma x, my sigma y, and my tau xy, those three values have to be on the circle. None of them are on the origin. Okay, so sigma 2 then, right, is going to be over there. And yeah, if it's, if I've got pure shear, then sigma 3 I'd probably say is at the origin. But it's at the origin not because of what's happening in the plane, but it's because of what's happening out of the plane. Okay? So now we have sigma 1, sigma 2, and what is the relationship between sigma 1 and tau xy? It's not a trick question.
They should be the same.
They're equal to each other, right? Yeah, so sigma 1 equals tau xy here, right? So sigma 1 is equal to tau xy, right? And we can say that this is equal to minus sigma 2. Okay? So now what we see here is that, okay, I've got sigma 1 equals minus sigma 2 is equal to tau xy. And this has got to be less than SSY, which is equal to 1/2 SY. So what this means is that sigma 1 and, I guess I can say, so let's say it like this. Sigma 1, that's not what I wanted to do. Sigma 1 and the absolute value of sigma 2. Well, I said, let's just say, and negative sigma 2, right, have to be less than 1/2 SY. Okay, and this is the case of pure shear. So what this means is that sigma 1, sigma 2, they have to be equal and opposite to each other, and they come out to this location, right? And if they're right on the threshold, or they come out to a series of locations on this line, right? But the threshold is when I have a situation where it hits this line on the border of the sigma 1, sigma 2 domain that is going to result in failure. So if I continue on this line outside, that means that sigma 1 and minus sigma 2 have become somehow greater than half of the yield strength. Can you see that? Like if I'm out here, as I go out here, if I continue on this line, this is a line of failure. Okay? And so we can figure out that this line represents, or the intersection of the pure shear line and this border represent the threshold for which we won't have failure. This border, let's do something else. This border has a value of sy, or minus sy over 2, sy over 2. That's just from here. Look, right? We said it has to be less than, sigma 1 has to be less than sy. Minus sigma 2 has to be less than sy. Right? And so that's where we are. Or wait a second. Or maybe, sorry. Blast. Okay. We're actually, so sometimes these plots get confused, or I get confused, better said. Okay, so we're actually, this is where we have positive sy over 2 minus sy over 2. So actually we're talking about this side. They're symmetric. Okay, they're symmetric, but this is, if you go outside of these lines, outside of this intersecting point on either side, that's where you have issues. Is that clear? Is that any questions on that? Over here, in these regions, it's just the box. Like that. Okay. And why does this make sense? Well, this goes back to what Kavya was saying. There's a sigma 3 probably at the origin. Okay? So imagine we're in this region or this region. We've kind of described, with pure shear, we've kind of described some of this, but we've only described this line, but let's just talk about what's happening over here and over here in quadrant 1 and quadrant 3. In quadrant 1, of sigma 1, sigma 2 plot, all the Moore circles are going to have a sigma 1 and a sigma 2, right, on the right side of the tau axis. So that's tau, this is sigma, then that means that I have, let's say, a sigma 1 out here, and sigma 2 could be anything. Let's just say sigma 2 is right there, arbitrarily. And if we assume that sigma 3 out of plane is at the origin, then the maximum shear stress is going to be, well, you tell me, what is the maximum shear stress? Huh? No, the absolute max. The absolute max. It's close. It's not sigma 1, but it's... No. Wait, what did you say? Sigma 2? No. Yes?
Does sigma 2 act as the midpoint of that larger circle?
It doesn't matter. Sigma 2 can flux anywhere between 0 and sigma 1. So what's the max, absolute max shear stress? Yes, Shane?
Half of sigma 1.
Yeah, it's just half of sigma 1. Do you see that, right? Because sigma 3 is at the origin. Okay, that's the out of plane component, that's 0. So the biggest circle, right, of the 3 more circle, the biggest one with the absolute max has to be the radius of the sigma 1, sigma 3 circle when we're in quadrant 1. Questions on this? So that means, okay, that and tau, right, and this has to be, and this, so 1/2 sigma 1 has to be less than 1/2 sy, right? That means that sigma 1 is less than sy. Right? So in quadrant 1, when we're over here, I can have anything up to sy. Right? So this point right here is sy, sy. I can have anything, I can go up here, you know, anything can go up to that value, right? And similarly, and it doesn't really matter what sigma 2 is, as long as sigma 2 is less than or equal to sigma 1, right? It can be anything that fills this box. But once sigma 1 or sigma 2 become greater than sy, then we have a situation where half of that value, half of sigma 1 or half of sigma 2, is going to be greater than half of sy, or the shear strength of the material. Okay. Questions on this? I wanted to cover this because I figured, you know, we went through maximum shear stress theory really fast last time. And in order to be able to understand what we're going to do today, I think it's appropriate to spend a little bit of time on this. Questions? Yes?
So when drawing a Moore circle for non-two-dimensional things, you draw the biggest circle between sigma 1 and sigma 3, which is almost always at 0, and sigma 2 can be anywhere in between.
That's correct. That's correct. Okay. Now, something that we're seeing here, and we'll talk about this today when we discuss distortion energy theory. Okay. If you fail from shear stress, what do we care about? We start to care about what the kind of the maximum difference in the principal stresses is. Do we see that? Right? Maximum normal stress was nice and easy, in that it just said, find me where, whatever the maximum normal stress is, that's what I care about. I don't care about any differences. Okay? I just care about, tell me which one is the maximum one. The maximum shear stress cares about, okay, find me essentially the largest span on the sigma axis, okay, if you're doing more circle. And that's going to dictate what the absolute maximum shear stress is. Okay? Often it's between, you know, often sigma 3 is equal to 0, but it doesn't have to be. You know, and in our case, a lot of our problems have had sigma 3 equal to 0. We're mostly operating in, you know, kind of 2.5D. Okay, and this gets to something though that's kind of interesting in that when you have this large displacement, and you know, what is shear stress? If we go back to what is shear stress is a shape deformation, right? That doesn't necessarily result, or not necessarily result of, you know, changing the length of a particular side, right? You can have pure shear, right? And we can figure out what the equivalent normal stresses are, but it's kind of like this gamma, okay, that's in there, that's resulting from this shear stress, okay? And so that kind of oblongation, if it's a word, okay, of the element is what is causing there to be failure from shear stress, okay? If I stick a cube underwater and it sinks to the bottom of the ocean, that cube has normal stresses acting on all 6 faces that are more or less the same. Yes, the cube can have some height, but that height's gonna be pretty small, let's say, right? It's not like I put a skyscraper underneath the water, okay? So the normal stresses are pretty much all the same. If a material like these ductile metals doesn't fail because of, or it only fails because of the maximum shear stress theory, when it's at the bottom of the ocean, what's the shear stress? Or what's the absolute maximum shear stress? I just told you that sigma 1, okay, let me rephrase it. Excuse me. Sigma 1 is equal to sigma 2 is equal to sigma 3, which is equal to a lot of pressure, rho GH. Okay, what does the Moore circle look like for sigma 1 equals sigma 2 equals sigma 3? Yes? A dot. So what is the shear stress associated with a dot on Moore's circle? 0, right? So this is why when the Titanic sinks, or when you have things that are under a ton of pressure, right? You take a submarine down there and it implodes, unfortunately, right? We had this happen last year, right? Then you think, oh wow, you know, materials are gonna fail, right? But if I take a block of material that's a ductile material and it just sinks to the bottom of the ocean, it's not going to fail because all three stresses, the principal stresses are all equal to each other, and the shear stress in it is 0. So this idea forms the basis of what we'll call a von Mises stress criterion in a little bit, okay? And that's from maximum distortion energy. So essentially, maximum shear stress theory also essentially says it's based on distortion. If the element distorts, that's when you're going to have failure, right? And even a uniaxial loading, when I do a tensile test, I am distorting the material, right? If I were to somehow magically pull the cube, right, apart, you know, I talked about it sinking to the bottom of the ocean, so that's all compressive. But if I have an ability to pull the cube apart in all, you know, in the 3 directions at the same time, the same amount, in theory, right, that material would not yield from maximum distortion energy. Okay? In practice, okay, we would expect something. Okay? All right. So now let's go ahead and get on to this stuff. I used all my extra time that I thought we'd have at the end on that, on kind of a review of the failure criteria 1. So today we're going to discuss safety factors at the beginning. We'll talk about the Moore criterion for brittle materials, and we'll talk about maximum distortion criterion for ductile materials. Okay, so these are 3 topics. Okay, this is a pretty important concept. Safety factors. And to kind of start us off thinking about this, when do you use safety factors in your daily life? Yes?
If you're looking to buy something that needs to support weight, you buy something that looks like it can support more than you need.
Okay, great. So this may be, to be honest, this may be not something I do on a daily basis, where I like, hey, I'm going to buy a shelf, and I want to make sure that, you know, the shelf doesn't break, and so I'm going to either design it or buy it, you know, and then make sure that my amount of force that I'm going to put on, the amount of weight I'm going to put on that shelf is less than whatever the manufacturer specifies, right? Hopefully, you're not doing a safety factor calculation if you're buying it, quote, off the shelf, unintended, okay? Because they've already done that, okay? They've already done that calculation for you. So if they say the maximum weight that this wagon or this chair can handle is 350 pounds, right? Hopefully their engineers have done whatever safety factor they think is appropriate, maybe 1.5 or 2, right? And so as long as you don't go to that amount, 350 pounds, whatever they specify, then you're good. Alright, so, okay, good. So in your daily life, when else do you use safety factors? Yes, huh? Bed frames, okay, yeah, so bed frames, similar concept. Let's back it out, let's not think about mass and weight. When do you budget safety in your communications with other humans? Like, just a buffer. What buffers do you use in your daily life? Yes, Andrew.
I don't know if this is what you're looking for, but let's say I have to get to class at a certain time, so I leave a little earlier to spare some time in case there's traffic.
Right, yeah, so that's the idea of a safety factor in another sense, right? So like, I know my class starts in 45 minutes, but I'm going to leave 60 minutes ahead, right? So what safety factor does that give me? Okay, that gives you, yes, good, so it gives you a quantity of 15 minutes, that's the buffer. And how would I, and I haven't really told you how you define a safety factor, we talked about it a little bit, but what's 60 divided by 45?
1/3.
Yeah, 1.3, repeating, right? So your safety factor would be something like 1.3. Okay? So this is kind of analogous to what we do in engineering, right? And in this case, it says mechanics, yes, we're talking about safety factors that could either be related to the forces that we're interested in making sure we don't exceed, all right, or torque, so those types of loads, right? Someone says, hey, the shaft can handle, I don't know, 10 Newton meters, all right? This bar can handle 1,000 newtons, okay? Jumbo the elephant can stand on this bar, and he weighs 1,000 kilograms, or 10,000 newtons. So that's going to be a larger bar, or I can have him suspended, or whatever it is, right? So sometimes we talk about safety factors in terms of forces and torques. In this class, it's very important, though, to be able to think about safety factors in terms of stresses. Okay, so I could have a force, or I could have a torque, a loading a structure, and then I gotta pinpoint, use my X-ray vision to figure out where that stress is a maximum in the structure, and then what do? I compare that stress to what the yield strength of the material is, okay? Or I compare it to the shear strength of the material, okay? So, here's kind of just, they're very simple equations, but they will nonetheless confuse me, all right? They don't confuse you, but they'll confuse me, all right? So one way to define a safety factor is, what is the force at failure divided by the allowable force? Okay, now those terms are even confusing in themselves, in my opinion, right? Because what is failure? All right? In this case, I think we usually think about it in terms of, this is when the thing actually fails mechanically. So like, this is, this is when the yield, when I calculate the, whatever the stresses are, and if it's just uniaxial loading, this is when sigma is equal to SY, is equal to the yield strength, all right? So this is like the force that is when it's going to actually fail. But then allowable, all right, that's when you say, hello, NASA, guess what? You really should only make sure that in operation, you get to this force, okay? So you better design your circumstances, your environment, your mission, whatever you anticipate this part to experience with force, this is what the allowable force is. And now I've budgeted a safety factor of whatever, 1.2 or 1.3, okay? Another way to write out, okay, so this is, okay, great. So the top one is force when the physical or mechanical structure fails, and this is the anticipated or specified force for operation. Another way is to, like we said, often in this class, we're gonna be looking at the stresses. Okay, so we gotta go down a little bit, right? So, what do you think? A sigma fail, right? That would be, like a sigma yield strength, a maximum shear strength, right? It would be the stress, right, associated with physical or mechanical structural failure. And then these allowable stresses, whether they're shear stresses or they're normal stresses, this is anticipated stress for operation. Okay. Pretty simple, right? We're gonna mess it up, okay? Don't worry, it's okay, we get some practice, okay? But it's just this over this, right? But then when you start coupling it with all the other things that we have to think about, like we were just looking at maximum normal stress theory and maximum shear stress theory, right? And you're like, okay, now I got one extra thing to balance. Another way to think about this, okay, is what do I have to multiply my allowable stress to equal my failing stress? Okay, so sometimes what happens is we think about, okay, how much do I have to multiply my current operating conditions to get failure? And so sometimes there's like a force in one direction and a force in another direction, right? Or there's a stress in one direction and a stress in another direction. For example, with a pressure vessel, if it's a cylindrical pressure vessel, then I have a sigma 1 and a sigma 2, and I have a pressure inside, right? So I crank up the pressure, sigma 1 and sigma 2 both increase by the same factor, and I have to think, oh yeah, okay, I multiply that pressure by this factor, and then I get maybe a maximum shear stress, okay, because pressure vessels are often made out of ductile metals. Don't see too many pressure vessels, at least, well, I guess you could call like a cistern or something, an aqueduct, a pressure vessel, right? Because you've got these concrete structures that you build and then you fill them up, and there's pressure at the bottom, right? And that could lead to failure. So okay, I sit corrected, but that pressure is hydrostatic, okay? And it's not the nice like. Well, I guess you could look at it as a cylindrical pressure vessel. Okay, fine. Anyway, but typically the ones we're dealing with in today's society are metallic and ductile. Okay. Safety factor typically going to be greater than 1, right? Otherwise, your design is not very viable. All right. So this is what we discussed here. Okay. And the wording is often confusing, as we're either increasing the physical load of endurance or reducing the allowable load. Okay, so as a designer, all right, you say furniture supplier, if you're building couches or beds or whatever it is, chairs, you're like, if you want it for that price, it's only going to hold this amount. I've either got to change my material or I've got to make it larger and heavier to be able to support more force, if that's what you like. Okay, so there are these trade-offs. Or you just say this isn't going to work for a certain, sure, like you have whatever 10 kids in your family. Don't put them all on the couch at the same time. Okay. All right. And then we talked a little bit about planned obsolescence a few days ago, right? Where companies and capitalism has led people to realize that they don't want you to only buy once in your life from them. Okay, they want you to buy multiple times. So there's not a financial incentive in some cases to have a very high safety factor, right? You want to operate at the margins and then you buy another one. I don't know. Are there some companies though? Can you think of? Maybe we shouldn't say this in recording, but yeah, maybe you can think of some companies that push the high quality, very expensive spectrum, right? Maybe jewelry, right? That's something that maybe you buy once, generally speaking, right? And So, you know, it's expensive already, and you don't want it to fail. All right. So, let's do an example. You have an ultimate compressive strength that is equal to the ultimate tensile strength, or the magnitude, you know, they have flip signs, which is 100 megapascals. And, you know, what is, under these depicted states of stress, which will be revealed, okay, what do we anticipate having with a safety factor of 3, okay? So, or actually better said, sorry, will this fail with a safety factor of 3? So immediately, if I say I need to have a safety factor of 3, and I haven't even looked at my designs yet, but I told us, or we were told, that we have an ultimate compressive strength, okay, of 100 megapascals, ultimate tensile strength of 100 megapascals. What does this mean? What's the maximum, and we're using a brittle material, and we're using maximum normal stress, what's the maximum normal stress I can support? What is going to be my maximum allowable normal stress? Before I even look at my design, what is it? No, this is the allowable stress. This is not the breaking stress. The breaking stress is 100 megapascals. What is the allowable? Yes.
100/3.
Yeah, it's 33, right? Or, you know, whatever. It's 33 megapascals. So now, right, I've got right, Fs is equal to this 100 megapascals divided by sigma allowable, and my sig allowable is 1/3 of that. Okay, is that clear? Again, these are simple concepts, but you know, I'll mess them up. So let's take a look at some scenarios now. If this will work. Okay, so well, what's the answer here? Before I do any more work. Will it break? Or will it fail? I say no, I see a yes. I say no. Well, what did we just say the maximum normal stress allowable was? 33 megapascals. What's the maximum normal stress in this situation? 50. 50 is greater than 33. It's going to fail. Okay? So we say sigma 1 is that. Sigma 1 has to be less than the sigma allowable. The safety factor, right, is 3. So sigma allowable is sigma ultimate divided by 3. And sigma 1 is not less than sigma allowable. Failure. Okay? See how this works? Okay. What about this one? Can anyone do it in their head? So first, what is this? What do we typically call this state of stress? Yes.
Shear.
Okay, and not just shear, but 100% pure shear. Okay? So this is pure, we don't say 100% shear, we just say pure shear. Okay? So pure shear, what does the Mohr circle look like? Yes.
Oh, wait.
No, but you're on the right track. So what does it look like? Kavya, think about it for a second. What does it look like?
A circle.
A circle?
Center around the origin.
Right, centered around the origin, right? So now, what is the maximum normal stress in this situation?
Sigma 1.
Right, and what is it equal to?
The shear.
Yeah, right, it's just equal to the shear, right? So, in this case, right, we draw the Mohr circle just like that. Sigma 1 is equal to 30 megapascals. Sigma 2, you could argue, is minus 30 megapascals, right? Is this going to fail or not? You say no, and I agree with you this time. All right? So yeah, yes. Why? Because 30 is less than 33, right? So sigma 1 is less than the sigma allowable, so no failure. All right, let's do another one. Okay, so what do we do here? Yes.
More circle with those two numbers as the reference point.
Yep. Yeah. So this one requires a little more work, right? So we'll go to it. So we go ahead. Where is the center of this Moore circle?
30 feet. Oh, the center.
The center. Where's the center of the Moore circle located? 15 megapascals, right? Yeah. 15 comma 0, right? Why? Because it's just sigma x, the average is sigma x and sigma y, right? Sigma x plus sigma y divided by 2. Okay, so I've got the origin, and now I've got this reference point, right? My point P or whatever we call it, right? And that's going to be, where is that going to be located? Where do you, I mean, more or less, where is it located? Yeah, right. So it's located more or less right down to the bottom right. Correct? Okay, because I've got my tau positive, right? So it's down, it's going to be down here. Okay, so here we go. That's where it is. That's the center. Okay, and so what do we got to do now? Yes, Andrew.
Calculate the radius and then add that to the center.
Yeah, so we got to figure out what the radius of this is and then add it to the sigma average, right? Okay, so the radius, okay, so in this case, okay, the radius ends up being 15 times the square root of 2. How do we figure that out? Well, we have, it comes over 15 this way, right? And it comes down 15 that way. So the hypotenuse is going to be, well, 15 squared root of 2 is a 45, 90, right? Or you can use Pythagorean theorem. Either way, 15 squared root of 2. So sigma 1 is equal to 36 megapascals. Will it fail? Yes, right? Because we said that our maximum allowable was 33. Pretty straightforward now, right? A few examples. It's kind of fun, right? All right, now we have, okay, so this is a homework question. If we have time, maybe we can come back, but it's, you have a similar situation, right? Here though, we say that we have sigma x equals 100 megapascals, sigma y equals minus 50 megapascals, right? And there's a yield strength of 200 megapascals. All right, so you know how to do this. Question 2, all right? And this one, though, all right, is going to use the absolute maximum shear stress with a material of yield strength SY. Okay, by what factor might we multiply thickness to ensure safety? Okay, so in this case, if we increase the thickness of the pressure vessel, will the pressure vessel be able to support more or less pressure? Yeah, go ahead.
Plus.
No, but we're increasing the thickness. Can it support more or, if we increase the thickness of the pressure vessel, can we put more pressure or less pressure inside of it? We can put more pressure inside of it, right? What happens to the stress in the walls of the pressure vessel? If I increase the thickness, what happens to the allowable stress? Or what happens to, maybe not allowable, what happens to the stress in the walls? Does it go up or down as I increase the thickness? Yeah, stress goes down, right? Which means that we can support more pressure. Okay? So what it's saying is we need to, let's say that they say there's a safety factor of 2, right? But the stress that we calculate, all right, by maximum normal shear stress theory, let's just say that it's, it's equal to the yield strength of, it's equal to the shear strength of the material, right? Which is equal to half the yield strength of the material, right, from a tensile test. If it's just exactly equal to, then I need to multiply the thickness by a factor of 2, right, to give a safety factor of 2. Okay, so what we have to figure out is, okay, what is the allowable shear stress? Okay, because we have SF is equal to, right? In this case, we have. This case is SF is equal to the right? This is, and so let's say if what we got to figure out, right, is we had to, what is tau allow? That's the question, right? So in this case, we have to do tau allow is equal to tau break over the safety factor. Or we have to multiply, the thickness, right? The thickness to get, and okay, so what we have to do, right? We have to multiply. Let's say that we have, we figure out what our operating shear stress is. Okay, and in a pressure vessel, what is the operating shear stress in a pressure vessel? Like, the maximum shear stress in that, in a pressure vessel. What is tau? Let's just say tau operating, or tau, which is equal to tau absolute max. What is that equal to for a thin-walled pressure, cylindrical pressure vessel? Yes.
There's no shear stress, is there? Or am I thinking of something else?
Well, this is a good question. Is there no shear stress?
State.
Huh?
Only in that state.
Right. In that state, there's not a shear stress drawn, but I had to figure out what the maximum equivalent shear stress is, right? And that's going to happen when I rotate the element 45 degrees, or I rotate 90 degrees on Moore's circle. Plus its absolute maximum shear stress. So, what is the absolute maximum shear stress for a pressure vessel? Yes, Josh. What?
PR over 2T.
Yes. So it's going to be, let's back out. You did it right. Okay. It's going to be sigma 1 over 2. Okay. How do we get that? Because we know from Moore's circle, I had this was my sigma 2, this was my sigma 1, and then this was my sigma 3 at the origin. Okay. Okay. And so what you just did is you said, oh, it's sigma 1 over 2. What is sigma 1 equal to?
Stress.
The hoop stress. Hoop, there it is, right? And that is
PR over
PR over T, right? So this is equal to 1/2 times the sigma hoop, which is equal to 1/2 times PR over T. And so, as Joshua just pointed out, it's PR over 2T. Okay. So what we have to do is we had to crank this. We had to multiply, by a certain factor, such that the operating stress, okay, is going to be equal to a allowable stress, which is equal to tau break over SF. Okay. Does that make sense? Any questions? That's why these it's like really simple, you think, safety factor really simple, but it gets a little nuanced. All right. So that's safety factor. Now let's talk about a new criterion for brittle materials. Again, there is not a single unifying theory for failure. I would suggest, though, that this is less, I don't know, I guess some mechanicians would argue. This is not like some unifying, trying to come up with like a unifying theory for quantum mechanics or not, or going beyond quantum mechanics, for general physics, right? This is not that. This is just for failure, right? Okay, the models here do not account for things like temperature, rate of loading, corrosion, processing, even fatigue. We're not even talking about that, okay? And we already know that, or we've already talked about how brittle materials, they often fail catastrophically. They're sensitive, okay? It's like, we have those cliches where, you're walking on thin ice with a particular person, right? Well, you don't say thin steel. You say thin, right? Ice is kind of brittle, so you don't know exactly what's going to happen. So there's a lot of variability, okay, and the ductile materials are less volatile, and we have two theories for them as well. So we have two theories. We're going to now cover the Moore failure criterion, and then we'll cover this other one in a little bit. Okay. All right. So, we already covered this. Oh, I forgot to bring chalk for everybody. I'm sorry. Okay. Who didn't get to break the chalk last time? Here's a good piece. Okay, sorry. I think it ended about here. Monsieur, did you get to? You got to? Yeah, okay, so, sorry. Next, if I forget, you can penalize me somehow. All right, so, so if we have a brittle material, our maximum normal stress theory was quite good when we assumed that the ultimate compressive strength and the ultimate tensile strength were the same. Okay. But we've said in the past they're not. Okay? They usually are not the same. All right, and this is again review from last time. Okay, typically the compressive strength is higher than the yield strength. Oops. Okay. So that means that down here, this sigma ultimate C and this sigma ultimate T, that we're going to have the magnitude of sigma ultimate C is greater than the sigma ultimate T. Okay. So that nice little box, okay, is something we're going to modify here. Okay, so Moore's failure criterion. This is good for situations where the brittle material has different ultimate strength and compression and tension, and you might use different tests to figure this out. So you gotta essentially do more than just a tensile test, right? So everything we've done in the lab was just pulling them apart. You'd have to do a compression test and figure this out as well. And when you look at a Moore circle, okay, this is what you would see, right? You'd see one Moore circle for the ultimate tensile strength and out of plane 0 stress at the origin. And you'd see, another one for a Moore circle with ultimate compressive strength, and again, out of plane equal to 0. And maybe you would do a torsion test as well, right? And there's the torsion test. And that would be a pure shear. So you do those 3 tests, and then you kind of say that's your envelope for failure. And then we transport this idea over to a sigma 1, sigma 2 plot, or sigma 2, sigma 1 plot, and we have these 2 regions, okay, where you have the tensile, right? This would be describing the tensile region, and this would be the compressive region. I guess I should have flipped these colors, because the green is tensile, anyway, purple, you get the idea. And then over here you have this idea of kind of this curved, right, line that would go between these points in this quadrant 4 and these points in quadrant 2. And then we usually go one step further and we make a linear approximation, okay, for this curve, like that. Okay? And so this is now what we call Moore's failure criterion. And it looks kind of like a modified version of the maximum shear stress theory, actually. Okay? But it's what we use for brittle materials. And if you have a linear approximation in these areas, we can figure out what the slope and the location of that line might be, right? So we're starting down what's the y-intercept, okay? The y-intercept would be down here, right? Where sigma ultimate c, assuming now sigma ultimate c is a negative value, right? So the y-intercept is down here on the sigma 2 axis, boom, right? And then we have a slope of the rise, okay? So the rise, how much is it like to this point, right? To this point, it's going to be sigma ultimate, and the negative of it, because this was a negative value, and the run is going to be sigma ultimate t. Okay. So now we can figure out what this slope of what this line is. We can also figure out similarly what the slope of and the location of this line might be, where the y-intercept is not negative, but it's positive at ultimate t, the sigma ultimate t. And we can figure out whether or not we are in the envelope, right? And what's the envelope? Well, the envelope is going to be, this region like that. Okay, so here we go. We have a sigma ultimate compressive strength. We have an ultimate compressive strength of 100 or negative 150 megapascals, and we have an ultimate tensile strength of 100 megapascals. It's a brittle material, okay? And now we're going to try to ask ourselves, is it going to fail? Look, it's our fun 50 megapascals again, okay? Well, in this case, and we don't have there's not a specified safety factor, all right? So it's a little bit different. So we've seen these before, but we're not going to have a safety factor, okay? And anyway, it's a little bit out of order, but let's do this one first. Okay, sigma 1 is equal to 50 megapascals. Sigma 2 is equal to sigma 3 is equal to 0. Well, what do you think? Is this going to fail or not? What do you think? The operating is just sigma 1 is equal to 50 megapascals. If I were to draw the sigma 1, sigma 2 plot, right, I'd have something that looks kind of like this, right? And so my question is the operating stress sigma 1, is it in that box? Is it in that envelope? Yeah, it's in that envelope, right? That's 100, 100 right there. And 50, 0 is right there. So we're not going to fail. We're fine. What about this middle one? Well, this one's a little bit more complicated. Oh, sorry. Yeah, that's whatever. That's the safety factor too. Sorry, I recalculated that out. Okay. Okay. So this one is interesting, right? We can say that we have a sigma 1 equal 30 and a sigma 2 equal minus 30. Okay, you see that, right? So this we said was pure shear, so now I know sigma 1's this and sigma 2 is that. So we ask ourselves a question, is that going to be above this line or below this line? And how do we figure out if it's above or below? What do you think? How do we figure it out? Yes.
You were saying before that the point in the middle of that line should be, the x and y variables should be half of the yield strength, right?
That is for maximum shear stress theory. This is for Moore criterion. Yes, I'm tempted to do that as well. But what do I have to do here instead? Yeah, Dylan?
You could try to plug in sigma 1 to that formula.
Yes.
And then compare the sigma 2 value you get to the sigma 2 value that you have.
Right. If I plug in sigma 1 into this formula, right, that will tell me where this sigma 1, where it is on the line, right? Right, that corresponds to this line if I use this formula, right? So if I plug in sigma 1 here, sigma 2 on the line is going to be equal to minus 105. Okay, so that, let's say that's like, that's like, yeah, we're like kind of, because this is the overall plot, so like I'm kind of like down here, right? Like, because I'm 1/3, right? Because this goes out to 100, so I'm 1/3 the way across. So I'm like kind of here, and that point is like minus, well, it's 30 comma minus 105 at the location here. But in my operating case, it's sigma 2 is minus 30 megapascals. So is my operating point in the envelope or outside the envelope? It's in the envelope, right? So I'm going to be fine. Okay. All right, so this is safe. Now, calculating a safety factor is not trivial here. Why is it not trivial? It's not trivial because now I have what you might consider to be an operating line of stress. Okay? Kira, you said a minute ago this is a situation where you have pure shear. Okay? So can I describe how the system behaves as a function of multiplying the pure shear stress? Right? And so what I have to do is I have to come up with a factor by which I multiply the shear stress I have here such that it touches the envelope line. Okay, and that will be my safety factor. Okay, so this is a little bit confusing. So what we're doing is we want to see when we multiply sigma 1, all right, by a value that we go outside of the envelope. Okay. Well, here's that envelope line, all right? Here's that operating line, okay? We've got to figure out, as we move along this operating line, when we're going to cross the envelope line. Okay. So, and we know that this is equal to, and sigma 2 is equal to minus sigma 1. So where do these two intersect each other? That's really the question, right? That's what we want to solve, because we have a line here and we have another line here, right? And we want to find where they intersect. So what do? We just substitute in. The easiest thing to do, right, is say, oh, okay, now sigma 2 is equal to minus sigma 1. I put in minus sigma 1 over here, and I solve for sigma 1. Right, so here we go. And so the intersecting is equal to 60. So what is my safety factor? What is the safety factor then? what do I have to multiply sigma 1 by to get to intersect? Yes. Yeah, it's a safety factor of 2. Okay. I have to multiply my current operating stress by 2, move it down to here, that's where it intersects, and it equals 60. Alright, so this is a little bit nuanced. Alright, in terms of how we figure out where we are. And you know, maybe it's not a situation where it's pure shear, maybe it's something else, like it's a pressure vessel, right? Where sigma 1 and sigma 2, right, they are related to each other, and it's a factor of, you know, it's a factor of 2 in that case. So you see, and they're both positive, so they'd be in quadrant 1, right? They'd be up here in this region, right? And there'd be a slope where either you're going this way or you're going up this way, but let's just say that since sigma 1 is the bigger one, right? The slope is going to be 1/2 times sigma 1 is equal to sigma 2, right? And then you got to figure out, oh, when does it hit that envelope? When do I intersect the envelope on this side, and that, you know, and how much do I multiply until I hit that vertical wall? Any questions? Okay. So, here's another question. So we have a brittle material, okay, and it's questioning whether or not we're going to fail according to the Moore criterion, okay, yeah, okay. So there were some corrections back in parts 2 and 3 of session 22. That's fine, but that doesn't apply to you. It's been corrected already, okay. And we're giving you a ultimate compressive strain of 150 megapascals and ultimate tensile strength of 100. And now we have a load, okay, that has a shear stress and it has a sigma 1, or it has a sigma x, sorry. So this is something you get to work on. Okay. We've now covered 2 criteria for handling brittle materials. What are they? Maximum normal stress and Moore's criterion. We've covered one criterion for shear stress, or for maximum shear stress in ductile materials. We're now going to introduce a second. And we already foreshadowed a little bit here that this is going to be based on distortion, right? We said, hey, if all the normal stresses are the same, it's not going to fail. It's when you have a difference in the sigma 1 or sigma 3, right? Sigma 1, sigma 2, whatever it is, when you have a difference between those, you have a shear stress that's not present when when sigma 1, sigma 2, and sigma 3 are all equal to each other. So, here we go, maximum distortion criterion. So the concept for maximum distortion energy was discussed, I guess, by Huber in 1904. It's also known as the von Mises yield criterion. It's also known as the Maxwell-Huber-Henke von Mises theory. Okay, so a lot of people have their fingers on this, and so if you hear Henke, if you hear Henke stress, von Mises, even Maxwell, but the Maxwell stress usually refers to something else, actually. So, but these esteemed engineers or mathematicians or scientists, they're the ones that are responsible for this distortion energy theory. We have also talked about the idea that materials can hold or withstand a certain amount of strain energy. Remember this? Just like we talked about springs and having a amount of energy, right, 1/2 k delta squared. We said, or 1/2 times force times delta, right, that was the energy. We said, oh, we can have a specific energy, okay, where we have a strain energy density that comes from multiplying the stress and the strain by each other and divided by 2, or the area underneath the stress strain curve. And in this case, what we're thinking about is that the material, when it fails, when it's a ductile material, it's going to fail because it undergoes some type of change in shape or volume. And there's kind of, we can calculate how much that energy is stored in the material. And again, we said, if that loading, though, is something where you have sigma 1, sigma 2 equals sigma 3, the material is not going to fail. So this is only going to fail when we have a case where, sigma 1 is not equal to sigma 2, or sigma 2 is not equal to sigma 3, or sigma 1 is not equal to sigma 3. Okay, that's when we could have failure. And then this is something that's kind of beyond us, but you can think of these types of systems where they draw these octahedral planes and there are equal stresses on them. Okay, we're not going to go dive into it that much. Okay, but let's go ahead and start with a strain energy density. Okay, if we have only principal stresses, okay, the state of triaxial stress, then we can say that the strain energy is equal to 1/2 sigma 1 epsilon 1 plus 1/2 sigma 2 epsilon 2 plus 1/2 sigma 3 epsilon 3. Okay, and remember, we're not saying that sigma 1, sigma 2, and sigma 3 are equal to each other, right? These could be, you could always get to a state of principal stress, right, in 3D, and that's the state of triaxial stress. So in this state, we've said there is no, there are no shear stresses on the sides of this cube. Now, another thing that we know is that there are stress-strain relationships from Hooke's law. And we can relate these normal stresses to their normal strains. Well, that could be useful, right? Because we have sigma 1s and epsilon 1s, right? We have, and now we can, if we relate them to each other appropriately, right, we can think of the strain energy just in terms of the strains or just in terms of the stresses. We're going to pick getting it in terms of the stresses. Okay, so we substitute these expressions in, and this is what you get when you do that substitution. Okay, so now we have a strain energy that is based on an elastic modulus, it's based on Poisson ratio, and it's based on essentially sigma 1, sigma 2, sigma 3. And there's the same equation going further. If we look at the hydrostatic components of stress, so hydrostatic components of stress would be the average of all three. Okay, so they're all, that's like, that's what they're all, we kind of conceptualize that they all are applying this kind of average stress plus or minus something. And the distortional components of stress would be how much, what's that difference? What's that plus or minus for each one of those principal stresses relative to the average? Does that make sense? So like, I've got some average stress, but like, my average stress is 50 megapascals, but in this direction I'm at 100 megapascals, so I have a distortional stress of 50. And in this other direction I've got a stress of 20, and so I've got a negative 30 distortional component of megapascals of stress. Okay? And now we say the yielding, this is only going to come from distortion. Okay, so yielding, that's the definition of failure. Yielding would be what? That's when we're going to cross these thresholds of yield strength. Okay? And yeah, we're just putting in these distortional components. We're looking at where they fall in. So we can think of a strain energy due to distortion, essentially. Okay? And this is the strain energy due to distortion. It comes out as being this kind of complicated expression. Sure, you could write it down if you want, the distortional strain energy, okay? And then you see that if I plug in, this is really nice, if I know my triaxial state of stress and I plug in my sigma 1, sigma 2, and sigma 3 into this formula, I can figure out what the distortional strain energy is. And if I'm above this distortional strain energy threshold, the specific strain energy density with respect to this distortional energy, then I'm going to have failure. So here's the strain energy due to distortion. This is what we just said. I can calculate the strain energy due to distortion by doing what? The tensile test, right? But what is the tensile test? Tensile test is that sigma 1 is equal to a quantity, but sigma 2 and sigma 3 are equal to 0. So I can figure out what what the strain energy density is, okay, due in uniaxial loading, all right? And then I can compare. So I do my tensile test, whoop, and I figure out, okay, it's 100 megapascals of stress. I now figure out my strain energy density is whatever it is based on the elastic modulus and the Poisson ratio, okay? And this is now my new strain energy density. For failure. And so I can write it out, okay, the same way. This is the yield strength, right? That's the strain energy at yield. And this is when we have failure when if I calculate out a strain energy, right, in an arbitrary system and is greater than the strain energy density yielding, that's when failure occurs. Any questions on this conceptually? Do you have to do this derivation ever again? Not in this class, maybe in another class. Okay. Should you write these equations down? No. All right. I'll show you the ones that you want to write down on the next slide. Okay. But the concept is powerful. The concept is taking what we talked about strain energy density before. It's introducing this idea that there can be a set of stresses that create distortion, and that we can kind of separate the overall strain energy density from the distortional strain energy density. It takes the idea that we can do uniaxial testing of a material with a tensile test, just like you did in the lab, and figure out what the associated distortional strain energy density is, and then we can compare for whatever system that we have the triaxial state of stress in, we can compare that strain energy density to a strain energy density, or add distortional strain energy density to the distortional strain energy density present when we did our uniaxial test. So this is the equation that you want to write down. Because look what happens. We've got this term and this term, okay? And you see there's like a factor of 2 between them, okay? And so we can come up with what's called an equivalent uniaxial stress with this equation. You see that? Maybe it's not clear. Essentially what we said is, where is, this is it's actually this equation and this equation, right? comes out to this equation down here. Okay, and this is saying, okay, this is the equivalent uniaxial stress, right? There's a uniaxial stress right here, and I set this equal to this. These factors disappear, right? So I'd have 2 sigma squared uniaxial equal to all this mess. Okay, and so now the equivalent uniaxial, right, is just going to be this quantity, we'll call it blah, divided by 2 square rooted. All right, where this is equal to blah. I wrote blah once like this, not for this particular example, but I had someone come up to me afterward and say, "What is variable blah?" No, I just meant big mess. That's all I meant. Okay, that's what blah is. Okay. Any questions? So this is an equation. I'll show you another equation that you want as well. All right, but this is the equation you want on your formula sheet. Now, what does this mean in terms of failure? What do I? So let's say sigma 1, sigma 2, sigma 3, that's a state of operation, right? So I throw at you, this is sigma 1, sigma 2, sigma 3, maybe sigma 1 is equal to 100, sigma 2 is equal to 50 megapascals. They're like, blast, why do you keep doing pressure vessels? Sigma 3 is equal to 0, right? Because the ratio is factor of 2 for sigma 1, sigma 2. Anyway, so then how do you tell me if you have failure or not? I give you a state of stress. Well, what else do I have to give you? I have to give you something about the material, right? I was like, hey, here's a state of stress. Does it fail? Well, you didn't tell me what material it is. You didn't tell me the yield strength. So how do I compare the yield strength to that sigma uniaxial? Yeah.
This is not answering your actual question, but by uniaxial, you just mean that all of the stress that is happening is only happening on one axis, right?
It's the equivalent uniaxial. So this is, yes, essentially exactly the tensile test, right?
Okay.
That's exactly right, right? I just have a tensile, I have one, it goes back to the bar, right? All these things today a lot, well, the last couple of days we're going back to our basic understanding of F over A for a bar. So yeah, it's just, there's one normal stress, all the rest of the stresses are equal to 0. Okay? So what you do is you compare, question is, yes, we compare, okay, and this is it. We compare the sigma y, we compare to sigma y or sy, all right? If sigma uniaxial is greater than sigma y, then failure. Okay, that's it. It's very nice. Now, what if you don't, what if sigma 3 is not equal to 0? Like sigma 1 and sigma 2 are not equal to, sigma 1, sigma 2, and sigma 3 are not equal to 0. And they're not equal to each other. You're like, oh man, that's not fun. That means I've had to figure out I1, I2, I3, right? And do the roots, right, of that general equation. And I already said you're not going to have to do that. Wouldn't it be nice if there was an equation that didn't require the principal stresses? Right? Now this is very nice if you know the principal stresses, and sometimes it's very easy to get the principal stresses. Okay, but if you don't, then you want to use this equation. Okay, so this equation is haven't really derived it, but I guess you could if you started looking at will it work? I was thinking you could like do the projections, like look at the sigma 1, 2, look at the 1, 2, the 2, 3, the 1, 3. I'm not sure though if that will work out exactly, but either way, the point here is that if you have a general state of stress, not sigma 1, not sigma 2, not sigma 3, but if you have sigma x, sigma y, sigma z, then you can calculate the uniaxial equivalent. This is a very powerful equation, of course, because it allows us to go mind numb. Okay, we can just like plug it into the calculator. What is my uniaxial stress? And be done with it. Okay? And once again, you can compare this equivalent stress to the yield strength of the material. All right, now, this is interesting too. There is an equation that will describe whether or not you're in or outside the envelope. Now you remember that we had we said that x squared plus y squared is equal to r squared, right? Does anyone know what this equation represents? It's not exactly fair. I wouldn't. But we have a sigma 1 squared plus a sigma 2 squared is equal to r squared. Then we have this cross term, a minus sigma 1, sigma 2. Any guesses? Yeah, Katia?
Is it sigma 1 squared plus sigma 2 squared, sigma 1 plus sigma 2 multiplied by sigma 1 minus sigma 2?
Oh, okay, yeah, so that you're thinking of FOIL, right? Yeah. So there's that idea, but that would be kind of, what are you thinking?
So like a circle or an ellipse or something?
It's like a circle and it is an ellipse, okay, in terms of what it graphically puts out, okay? And so, I guess I don't have it. Let me just draw what it is. Okay. The ellipse is not your kind of nice, how do you say, ellipsioid, how do you say, it's not a nice ellipse like that. It's aligned with the x-axis, the horizontal. Okay, the way this comes out, and often it's kind of, you draw, and you'll see this, we draw a little bit like this. Okay, we're going to say, all right, it comes out, and we have this point, this point, this point, this point. It's an ellipse that does like this. Oh, guys, that's one of my best ellipses. I know, it looks really bad, but that's really actually pretty good for me. Okay? You see that? So it has a major axis, okay, that goes along the slope 1, okay, and its minor axis is on the pure shear line. Okay. So this is the, you're safe inside the ellipse. So now, if you're given a situation, you might have to figure out, okay, I've got a load line, when do I hit the ellipse? That's a little bit more tricky, okay, of a problem. But a pure shear problem is not so bad because it hits the pure shear line at the square root of 3, okay, sorry, I can figure things out. Okay, so that's where it hits the shear line, okay, down here, and up here it hits the shear line at minus square root of 3 over 3 sigma y, comma square root of 3 over 3 sigma y. Okay. Alright, so that's kind of another way to map out the sigma 1, sigma 2 plot. Any questions on that? Okay. So let's do an example. Okay. Let's say we have an SI or sigma y. You'll just see both of them. I think Hibbler often prefers SY. I'm not sure actually, or maybe it's Juvenile. I can't even remember which book prefers which. But you can see them both. SY is nice because it doesn't require you to hit insert equation editor in Microsoft Word, right? Anyway, okay, no, that wasn't a funny joke. All right, so the question is, will it fail under the depicted state of stress according to the von Mises criterion? So what do we need to do? Well, what would you do? Knowing what you know now, how would you solve this problem? Yeah, Andrew.
Put it into the general state of stress equation.
Yeah, that's the easiest, that's the most mindless way to do it, right? Okay, how else could you do it? Which would be slightly more slick. Or maybe not that more slick. But what's the other way to do it? Someone else? I know you guys are, yeah, I know you guys know. Josh, what are you thinking? How else could you do it?
Draw the Moore circle to find the ultimate strength.
Okay, so let's rephrase it. You can,
Ultimate stress.
okay, to find the state of principal stresses, right? This is just a 2.5D problem. So sigma z is equal to 0, tau yz is equal to 0, tau xz is equal to 0, right? So what we've got here is just a sigma x equals 90 megapascals, a tau xy equals 30 megapascals, sigma y is equal to 0 too, actually. So what you're saying is, I can figure out what my sigma 1 and my sigma 2 might be, right? And I already know that sigma 3 is equal to 0. And so once I've got those, then I've got sigma 1, sigma 2, sigma 3, and I can plug that into the other equation for figuring out the equivalent uniaxial stress. Okay, so there are two ways to do it, right? Here, so this is the equation we're talking about. Or you can use that equation, right? So you can use either one. But if we use the Moore circle to use the upper equation, okay, we can figure out the radius of the circle, and thus we can figure out sigma 1 is equal to these quantities like that, right? Because it's going to be the radius plus the average, right? What's the average here? It's just 45 megapascals, right? Because the sigma y is equal to 0, and the average minus 45, okay? So once we know the principal stresses, all right, we can figure out the equivalent von Mises stress like this. Okay? Or if you want to use the original stresses, kind of not thinking too much, you can just plug those values in like that. So if you have time on an exam, and we've got to calculate the von Mises, you might check yourself by making sure that both of these are equal to each other. Okay. What was I going to say? Oh, that's what I was going to say. So you've done a little bit of finite element now, right? Remember? And maybe you've done some others. Maybe you did it in SolidWorks. If you look at one of the options, this equivalent stress is so powerful that, and it's so mind-numbing, because look, it tells you the stresses for any state of, it gives you one number, right, that you can compare to the yield strength that tells you whether or not you're going to fail by the von Mises criterion. So finite element packages, pretty much all of them, tell you what the von Mises stress is. So there's an option, so you can look at, so the coloring of the elements, right? You can have it spit out a coloring that's the von Mises stress. You can actually also have it, usually you can also have it spit out a coloring for Tresca. And Tresca, right, is just going to be the maximum shear stress. Right, so that's going to be going through and figuring out, okay, what's your tau 1, tau 2, tau 3, and I'll figure out what the maximum shear stress is. The absolute max. All right, let's go on. I had to walk over here since this thing is not clicking. All right, Tresca versus von Mises. Okay, now you see sigma 1 and sigma 2, they're flipped here. Okay, so it doesn't matter. Okay, you can you see they're both symmetric. So sometimes you'll see sigma 1, sigma 2 like this. Other times you'll see it where they write them with sigma 2, up there and like that. All right. So which one has the larger envelope? The von Mises, right? So, this means that the von Mises is going to actually, if you can satisfy von Mises. Sorry, let's put it this way: you can satisfy von Mises, but not satisfy Tresca. Right, you see that? So this kind of suggests, right, that that if you want to kind of push the envelope, you use von Mises, all right, to be able to, essentially say that you can handle more stress than you can handle in Tresca. It also means that if you use Tresca, you're probably going to be okay. And Tresca actually, in a lot of cases, is simpler, right? You can do the more circle and boom, you're done. Okay. We talked about the line of pure shear already and where they are. All right, so in Tresca, it's at minus sigma 1 over 2, sigma 2 over 2, like that, right? And here it's at the sigma 1, the square root of 3, sigma 1, comma negative square root of 3, comma 3, over 3, sigma 2. Okay. Okay. All right, so what is the safety factor under the depicted state of stress according to the Tresca criterion? And what is the safety factor according to the maximum distortion energy criterion? Okay. So here, right, here's Tresca. And this is a pure shear, right? So now we know that we're going to be at 1/2 sigma y, comma minus 1/2 sigma y, all right? And if it's pure shear, we're moving along this line. The intersection of these is going to be at 50, comma negative 50, all right, down here. So we see sigma 1 is equal to this, sigma 2 has got to be equal to that. So what's the safety factor going to be here? It's going to be 2, just like that, right? We're essentially moving from this point right here to this point right here. Okay. What about with the von Mises criterion? Well, we said this is going to be square root of 3 sigma y, comma minus square root of 3 over 3 sigma y. The intersection is at 57.7 minus 57.7. So the safety factor is a little bit higher. It's going to be 2.3. Okay. If you had just a normal stress, right? Let's say it was just a normal stress and you're like at this point and you're at this point. Do you see that Tresca-cito and Tresquita and von Misito, all right, they are going to intersect. They are the same at sigma 1. Or sigma 2, right? Or like along this, they're the same. Or along this, they're the same. They hit the same point. So in that case, if you have just uniaxial loading, Tresca and Womises will predict the same thing. Similarly, they'll predict the same thing if you have sigma 1 equals sigma 2, right, along this major axis of the ellipse associated with von Mises. Okay? That's where they'll predict the same thing. So they predict the same thing when sigma 1 equals sigma 2, or when you have just a 1 sigma 1, or like, just a uniaxial. All right. Okay. So is the criterion or Tresca, or which is more forgiving? Well, if we have, all right, so let's just try to map all these out. Maximum normal stress, it's a little bit hard to compare them because they're for brittle materials and they have different, often these ultimate compressive or ultimate tensile strengths are higher than the yield strength of the material, okay? But even if they're the same, you see that the maximum normal stress is bigger. Like even if I move this to here and I move this to here, I still would carve out this region and this region right here. Like I would still be carving out more. Ha. Get it? Never mind. So bad. Actually, I'm not carving out MOHR yet because I haven't done the Moore criterion. Okay. If you have the Moore criterion, chances are you have a higher compressive strength than you have than ultimate tensile strength, right? And so the window could end up being larger, okay, depending on, but it's going to be a mix because like this curve could outdo, depending on what the ultimate compressive strength is and the ultimate tensile strength are, it could be outside. Okay, so maybe it's a little bit unclear, but you could say that the Moore criterion would be more permissive, and then if you have it just depends. If you're using the Moore criterion and you wouldn't necessarily use it though. It's usually used when the compressive strength and the tensile strength are different. But anyway, you could also say maybe it's not going to be. All right, and if you have maximum distortion energy, right, that will be more permissive than the Tresca criterion, right? Is this kind of clear? Like, look, these are essentially what we're saying is these are the 4 criteria that we've discussed. This is how they could potentially overlap. All right, and you might need to do some rearranging based on what the ultimate compressive, ultimate tensile strength are versus what the ultimate yield strength of the material is. For the homework, you get to go back to a similar situation that we've seen before with loading, okay, and then use von Mises as a safety factor, figure out what that safety factor would be, right? And this is what we did today. We covered safety factors, we covered Moore criterion for brittle materials, and we covered maximum distortion criterion for ductile materials. Any questions? Yes.
Can you point out again one more time in the chart with all of them, which ones are for brittle and which ones are for ductile?
Oh, yeah. So the max normal stress, this is brittle. Moore criterion, this is brittle. Okay. Max shear stress, this is ductile. And the von Mises is as a ductile.
Thanks.
Okay, good. All right, so we'll go ahead and we'll end here. Thank you for sticking with it.